Okay, we're going to start with a review because this is probably one of the most important things that we learn all year. The first thing is our function is actually this curve right here. That's our function. The red line is what we're calling a secant line, and the slope of that red line is what we have here in this red box. We all know how to do a slope of a line that goes through 2 points. So first let's look at those 2 points. Our first point is x and then f of x. That's right here. Our second point is x plus h and f of x plus h. And when we say plus h, we're just saying plus a little bit more. Okay, if you remember the formula, it's going to be y2 minus y1, that goes on top, and then x2 minus x1, that's what goes on the bottom. And of course the x minus x cancels, so there's just an h left on the bottom. Now the slope of that red line goes by a few different names. Sometimes it's called difference quotient. So if you see that, that's what they're talking about. Sometimes it's called average rate of change from x to x plus h. But the slope of that red line is what we did in middle school, it's what we did in algebra and some of the beginning high school math classes that we took. Now that we're in calculus, we're going to do the slope of the tangent line, that's the purple dotted line. In order for that to happen, we have to do the limit as h goes to 0. Remember, as h goes to 0, this x value gets closer to this x value, so this point keeps getting closer and closer and closer to that first point. And that means the slope of this secant line keeps getting closer and closer and closer to the slope of that tangent line. So this is the big formula we're going to use. It's the most common one. Okay, here's another example. Instead of having an x, we have a 1. So for this example, when we do the limit as h goes to 0, we're not finding the slope of the tangent line for any value of x. We're finding the slope of the tangent line at x equals 1. Another way of saying the slope of a tangent line is derivative. A derivative is the slope of a tangent line. Okay, again, this is still just a review, but I wanted to point out that this is actually a different formula than the first two. The first two formulas were basically the same. It's just on one of them we used x, the other one we used a specific value. So here, instead of using x and x plus h, we're using c and we're using x. But everything's done the same way. We still have 2 points, c, f of c, that's right there. And then we have x, f of x, that point's right there. For the slope of the red line, that's the slope of the secant line, we have that formula in the red box. Again, this is called a difference quotient. It's also called an average rate of change. Now that gives us the slope of that red line, but what we really want in calculus is we want the slope of that purple tangent line. So we have to do the limit as x goes to c. Again, this is just a review. But as x gets closer and closer to c, this point gets closer and closer and closer to that first point. And that means the slope of this secant line gets closer and closer and closer to the slope of that tangent line. So instead of doing the limit as h goes to 0, we're doing the limit as x goes to c. Okay, in this section, one of the things we're trying to do is we're trying to recognize a limit as a derivative of some function. Here's our first example. If we use the most common definition of a derivative, and we plug in the function 5x to the third, we would get this. And so I'm calling that the correct one. If you see that limit, that's just the derivative of 5x to the third. Now the one that I'm calling bogus, which is not the derivative of 5x to the third, is an incorrect use of all three formulas. It's a mix of all three formulas. You see we have the limit as x goes to c, and on the bottom you have x minus c, which would be okay as long as the top would have to be f of x minus f of c. And it's not. So what we have on this example is we have the correct top that goes with this formula. But these two things go for the other formula. So this limit is not the derivative of 5x to the third. Now this limit still might have an answer, but it's not the derivative of 5x to the third. Here's another example. If we chose c equals 2, we would put a 2 for all these c's. And for the function 5x to the third, we would plug 5x to the third, but the x would be a 2 instead of an x. So we would take our function. We still need the number plus the h, so we have 2 plus h. Then it's minus f of c. So we're going to do minus f of, and instead of the x, we put our c, we put a 2. And then all over h. So this would be the correct limit that's equal to the derivative of 5x to the third. This bottom one is not the derivative of 5x to the third. You might notice that the top is done correctly, but the bottom is supposed to be an h, and we have x minus 2 on the bottom. We also have the limit as h goes to 2. That's not correct. It's supposed to be the limit as h goes to 0, so don't be tricked. Here's another example. We're going to use our third formula. We're going to still use the function 5x to the third at a particular value of 2. So all the c's get traded for a 2. This is still going to be f of x, so we still have our x on that one. So this would be the correct one on top. Because this one on the bottom is not the derivative of 5x to the third, I'm calling it bogus, but it's still a limit. It probably still has an answer, but it's not the derivative of 5x to the third. What we're trying to do in this section is we're trying to recognize a limit as just the derivative of some function. In the next section, we're going to learn how to quickly solve the derivative of these functions in about 3 to 4 seconds. So instead of doing these long limits, we're recognizing that they're just the derivative of a function, and then we'll just get the answer by quickly doing the derivative of the function. Again, the reason why this bottom one is bogus is because it has an h in the bottom. It's supposed to have an x minus c, so it's supposed to have an x minus 2. Okay, here's another example. What does this limit represent? Again, I think the trick is to try to ignore the h. If you ignore the h, you would have 5x squared minus 3x. And if you take a negative out of the second part, you get minus 5x squared minus 3x. So you're seeing the same thing twice, 5x squared minus 3x. That's the function that we're doing the derivative of. So this limit is the derivative of 5x squared minus 3x. That's a derivative that we can solve in about 3 seconds. But we'll learn how to do that in a later section. Okay, here's our last example. Again, if we ignore the h, you can see that we have 5x squared, but our x is 10. Then minus 3x, again our x is 10. So this is probably the derivative of 5x squared minus 3x when x is 10. We have to check it. We got to check this number. If we plug a 10 into our function, do we get 470? Plugging in a 10 gives me 500 minus 30. And that is 470. So that means that this is f of x plus h, and this is f of x, but when x is 10. So the answer to this one is that this limit is the derivative of 5x squared minus 3x when x is 10. Again, that's a really easy derivative to solve. We can do it in about 5 or 6 seconds. And we're going to learn how to do that in a later section.